Hi, and welcome to today's episode of Flip Notes, Types of Forces, aka Intro to Forces. The first thing in Unit 4 that we want to start off with, since we are talking about forces, is that we need a general definition of force, symbolized with the variable capital letter F. The definition of a force is as follows. It is a push or a pull, which you guys probably learned in previous classes, but for this class, we'll add to it to make it more specific and direct. It's a push or a pull that has the ability to cause a change in motion. The fact of the matter is that forces are always present. However, depending on the magnitude and the direction of the forces present, they may or may not cause a change in forces. Our objective here is to be able to identify and diagram all forces, whether they cause a change or not. Speaking of forces, we need to move on to the unit of measurement of force. The gentleman that you see in the picture, most of you know, is Isaac Newton. So the unit of force is named after Isaac Newton, capital letter N. As you found out in the previous day's lab, you should have discovered that 1 Newton is the amount of force it takes to cause 1 kilogram of mass to accelerate at a rate of 1 meter per second squared. The relationship in the lab with your spring scales should have been 1 Newton of force for every 1 kilogram of mass. And that's where our unit is derived from in part. When we talk about forces, we have to acknowledge that they are vector quantities, which from Unit 1, a vector quantity means that that quantity has a number, the magnitude, the size of the force, numerical value, and it will also have a direction, which could be positive or negative. As a review, for sign conventions, positive could be things like up or forward or to the right, while negative could be directions like down, backwards, and to the left. Your general force equation is worth copying down on your notes, so if you could find a blank space, possibly towards the top of the paper. Our general force equation is F equals M times A, which we will visit as we move throughout the unit in several different forms. In physics, force is a noun. It's something. It's not an action. Whenever we talk about forces, we have to acknowledge that forces come in pairs. Forces typically come in pairs. Whenever there's an action, there's going to be a reaction force. For the up, there's usually a down associated with it. Many of the forces that we're going to go through on Roman numeral 2 types of forces are contact forces, but you don't always require contact for the force to have action on its intended object. So we'll have categories of these types of forces we have listed on the front and back of your notes as contact forces. Some of them are non-contact forces. When we talk about what a contact force is, it's going to be a force that actually has to touch the object that it's acting on. In some textbooks, they call it the dealer and the feeler, the two objects that have to be in physical contact for the forces to interact. But we also have the other category, which can be known as non-contact forces or field forces. They can act at a distance. Think for a moment, out of your forces that we're going to go over today, letters A through G on the back of your notes, which ones seem like they would be contact forces and which one seems like it would be a field force? If you answered gravity as the field force, then you're right. Let's talk about gravity first. Go ahead and on your note helper, let's resume filling in the blanks. For gravity, the symbol that we'll use is F subscript G. Gravity is also commonly called weight. As you should have noticed in the lab, the link between mass and weight is that all objects will have mass. That's the amount of matter that is contained within the object. However, weight in newtons is simply the mass responding to gravity. We symbolize weight as Fg, gravity force. The equation for weight in physics is Fg is equal to m times g. M standing for mass, we always input that number in kilograms, and g standing for gravity, which on Earth we will accept to have the value of 9.8 newtons per kilogram on Earth. You will be tested in several scenarios where we have objects that are not on Earth, in which place you would have to input the gravity for that planet. And you'll have practice on that on Friday. Force number 2 is signified with the variable F subscript n, which is called the normal force. Normal force comes from a solid supporting surface, and this is a contact force. It has to be in direct contact with the object that it is supporting. The normal force is always going to be perpendicular to the supporting surface. A popular example of this would be when you have an object sitting on the table. The surface itself, that would be the table, is what exerts the normal force on the book. Again, since we said that the normal force is always perpendicular to the supporting surface, looking at the diagram, if you can follow my mouse, here's the supporting surface. The normal force is the upward force, and yes, as the notes say, it is perpendicular to the supporting surface, which would be the table in this case. If you can think back to what we talked about before in the PowerPoint previously, we said that forces come in pairs. So this picture is a good example of a pair of forces. We have the normal force supporting the book upward, and we have the weight of the book itself pushing downward. These two forces happen to be in equilibrium, which means they are equal in magnitude. See the size of this arrow compared to the size of that arrow. Equal in magnitude, but opposite in direction, which makes them cancel each other, which we can say these two forces are in equilibrium. Just because there's no change in motion doesn't mean the forces don't exist. It just simply means that they are balancing each other out. Before we leave normal force, I'd like to show you another example of a normal force, a more non-traditional example, and that would be this picture here. This person that has wedged himself up between two walls has a normal force supporting them. We can say in this case, the normal force is still perpendicular to the surface. If the surface is the wall here, the normal force supporting the person would be perpendicular to that surface in this case. So we're more on a horizontal axis compared to up top, we were vertical. Flip your page. Force number 3 is called the applied force, symbolized with capital letter F subscript A. Applied forces are applied by direct contact, again, another contact force, by an object or by a person. We can have an object provide the applied force, or it could be the person. In the picture on this slide, you have a person applying a force to the left on the desk. We don't know if it's causing a change in motion, but again, that force is definitely present, whether it causes a change in motion or not. Let's go to letter D and talk a little bit about friction force. Your symbol for friction force is capital letter F with a subscript of a lowercase f, or you can symbolize it with capital letter F and spell out the abbreviated word frict, F-R-I-C-T. So with frictional forces, we can always identify them because they are always in the opposite direction of the motion of the object. A force on an object moving through the, I skipped ahead. Frictional force always goes in the opposite direction. In other words, it opposes the motion of the object. Now, how much frictional force is present depends on the type of surface. If you can think about surfaces like tile floors or ice or glass, they tend to have a low coefficient of friction. But when you think about other surfaces like carpet or sandpaper, or a gravel road, they tend to have a higher coefficient of friction. So the amount of frictional force totally depends on the surface. Whether the frictional force is great or small, it will slow the object down a slight bit. Pressure between the surfaces will also determine the amount of friction. When you think about pushing an object across a floor that has ball bearings underneath the object or wheels, that's going to change the amount of pressure compared to if you're just pushing it with no assisted devices. Tension force, letter F, is signified with the capital letter F. Oh, I skipped ahead again. Air resistance is signified with the capital letter F with the subscript air. In previous units, we have ignored air resistance, but now we are going to bring it into play because as we talk about forces, the amount that air resistance would decrease the other forces that are present, we can take that into account now. It's not so negligible. Air resistance is defined as an upward force on an object moving through the air that will oppose the motion of an object. For falling objects, like in the picture, the motion is down, therefore the air resistance would be up. Air resistance is most noticeable for objects traveling at high speeds. There it is in the last bullet. For objects traveling at high speeds, which would be something like a skydiver or a downhill skier. Or we start to notice lots of air resistance when we get into objects with large surface areas, like this parachute. Last but not least, tension force, symbolized by capital letter F, subscript T, is defined as a force that's transmitted through a string, rope, cable, or wire when it's pulled tight from opposite ends. You can usually identify that a tension force is present as soon as we start talking about a rope holding up an object or cables or wires. In future assignments, we're going to start off slowly by, now that you have this database of the types of forces that we'll encounter in this class, we're going to give you several scenarios and hope that you can identify which force or forces are present. Again, a good rule of thumb for tension force would be whenever you have any of these yellow objects mentioned in the scenario, tension force is probably at play. Number 7, letter G on your notes, goes with the spring force, F subscript spring. And here is what we use for that. Spring force comes from the compression or stretching of a spring by an object. Compression or stretching of a spring. Anytime an object stretches or compresses a spring, it's always acted upon by a force that will restore the spring back to its rest position. Wherever it started, that restoring force takes it back to its original place. So there you have it, your introduction to forces. You have a word bank and database of all the forces present. From this point forward, we will practice identifying the forces that we've discussed in today's flip notes. See you on Friday. Have your notes ready.